Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Alright, let's step on inside, and we are going to be dealing with, in the Big Ideas Math textbook, section 1.3, inverse of a function, and everything else involved with it. So, let's take a look in the lecture section of the textbook and see what's going on. We will find inverses of relations, explore inverses of functions, and find inverses of functions algebraically. Now, I want to separate what a relation is versus a function. A function is a specific type of relation. Consider a relation to be any set of points that work together. If you have them in a table, if you have them on a graph, whatever they are. They can be a curve, they can be discrete, all that, but they don't have to be a function. Remember, functions need to pass the vertical line test. That's basically what they are. A function is a relation where every input only has one output. So when they say explored inverses of relations, kind of the same biz, only there's probably not an equation written in function notation that's going to be giving you that. Whereas functions, they will be, and we'll go from there. And then just a heads up here, let's see what they're going to say next, because I kind of sight read it. Okay, they're not really talking about that. So let me just bring something else up before I talk about that. You know, inverses appear in all walks of math, and when you hear inverse, you might think of different things. It depends on what you're talking about. Addition's inverse is subtraction. Multiplication's is division. Powers have roots. Exponentials, as in within x in the exponent itself, have logarithms. They're all over the place. So the kind of inverse we're talking about, inverse of a function, means we're talking about an input giving an output. Inputs and outputs are also inverses of each other. So if you find the inverse of one, you kind of get the other as a result. And that's what we'll be dealing with here. So, a relation pairs inputs with outputs, kind of the thing I said, that it's a set of points. It has an x comma y, and so there's an ordered pair with it, if that makes sense. An inverse relation switches the input and the output. So as I said, inputs and outputs are inverses of each other. X takes y's place and y takes x's place. Or as they say it, with a point a comma b, the inverse is b comma a. They switch places. They don't change signs. 2 comma 3 becomes 3 comma 2. Or you can see these examples right here. Of course, that's why we do this lecture part first. They give the examples. -4, 7 becomes 7, -4, blah, blah, blah. You see them as ordered pairs. And here you see them in a table where originally if the input is these 5 numbers, -1 to 4, now they become the output. And these increments of 5 as the output now become the input values. So they just swap, and then you can graph them as such. Okay, so that's the basic idea. And you could play with another example, find those inverses, swap the x's and y's, swap the x's and y's. Make sure they still tie in with the same ordered pair. So you should have a point a comma 0, and you should have a point here like 4, 2. Okay, moving on forward. Writing a formula for the input of a function. So now you see something that's in function notation right here, f of x equals, which means when I plug in a specific value for x, doesn't matter what, but when I plug in some value for x, I only yield a very specific y value. I can't get different ones. So inverses of functions now are something we're going to talk about. Or writing a formula for the input of a function. So if f of x, or y, is your output, and x is your input, how could you use the output and make it be the input? And make the input be the output? Instead of making it say y equals, you make it say x equals. Now remember, this did say f of x to begin with. The best thing you want to do in this case is turn it into a y, just a single variable that seems to be able to manipulate with other parts. It's no longer a function bit of x because now x is a function of y, so it's better to kind of do it the other way. Turn it into y and then solve for x. Use the inverse operations to do so. +1, do -1 on both sides. X times 2, divide both sides by 2. And now the input becomes an output x. And you get x by doing y minus 1 over 2. Now you can plug values in for y to get values out for x. And that's one of the ideas and concepts of an inverse. If you want to find the input when y equals -3, see, I could substitute -3 right here. -3 equals 2x plus 1 and solve. But you'd have to do it the same thing over and over where you have a formula applying to it right here. And you can kind of do it the rest of the way pretty easily. So that's one concept, and it moves forward. Let's see if there's anything else on this page I really want to pay attention to there, because we'll do examples with it. Just solve for x instead. Looks good. Let me show you this graph here. What's in blue is that original y equals 2x plus 1. And what's in red is it did say x equals y minus 1 over 2. But what we're going to do in this case, and let's see if they actually show it. Not really. See where it said x equals y minus 1 over 2. Now we turn the y into x again, so we place it on the same graph and represent what the inverse looks like graphically. The blue is the original function. The red is the inverse of the function. In this case, it also happens to be a function. That's not always the case. But this is the inverse of the function. How do they relate to each other? Well, if you notice, the points are inverses of each other. What was 3 comma 1, what was 1 comma 3 is now 3 comma 1. What was 2 comma 5 is now 5 comma 2, and all that. And you see this dotted line, this is the line y equals x. What this is showing is that any graph can be reflected across the line y equals x, and you're going to represent its inverse that way. So you kind of got to tilt your head that angle and see that there's a true reflection of that. And that's what happens with inverses. Okay, to actually find the inverse of a function, the steps that you kind of saw before apply, and then you swap the x and the y when you're ready to take its inverse. So how do you find the inverse of a function algebraically? Step 1, we're going to set y equal to f of x. Basically, replace f of x with y for the reason I stated before. It's more manipulative as a variable, and it's no longer represented as a function of x. So you notice here on this step 1, f of x equals, turn it into y equals. Step 2, let's create the inverse portion itself. Swap x and y. Your goal is to rewrite this to get y by itself again, so it can be mapped in the same format, and when you have the inverse with your original function, now they're both a y equals set. It's a different equation. It is the inverse. But your goal when you swap them is get y by itself again, and then you've created the inverse equation, and that is step 3, solve for y, using inverse operations. So step 1, swap f of x with y. Step 2, swap x and y. Step 3, solve for y again. In this case, add 9, divide by 4, and boom, you have an inverse equation. They haven't written it here, and I don't know if they will. It seems like it's probably not represented in the book. I'll show it to you in case you ever use it. In inverse notation, if f of x is your original function, this right here is known as the inverse of it. So inverse of function, and here's the original function itself. It looks like it says f to the negative first power. That is just the notation. It's not what it means. Negative first power has a different actual thing to it, but that's inverse notation, if you will. You can represent it with anything. You can put g of x equals, as long as it's still a function, you can keep it as y equals or turn it into this. If I ever do this, not by accident, but by habit, then at least you understand what I meant by it. See, what it at least tells you is it's the inverse of that one. Okay, moving forward, and it looks like that's the end of the notes for that portion there. So I'm going to go ahead and do this vocab and core concept check, and then we'll do the problem sets, and it's a lot smaller. I think it's 3 to 31 for this problem set. Okay, number 1, complete the sentence. A relation contains the point -3, 10. The blank contains the point 10, -3. If you compare these two, you'll see that they traded places. -3 was the x, now it's the y. 10 was the y, now it's the x. When x and y switch places, you are referring to the inverse. It's just a vocab check. They're trying to warm you up and not trick you too much. Number 2, different word, same question. Consider the function f represented by the graph. In this function here, it's these 4 points at least. Which is different? Find both answers. So graph the inverse of the function. I don't know if they're asking me to do it. I'm not planning on doing it unless I have to. Reflects the graph of the function in the x-axis. Okay, those are different. So here, let me say this. If this is A, and then this is B, meaning those are different. Anything else that I mark that's the same as B, I'll put as B, and anything else that's the same as this one, I'll put as A. Reflect the graph of the function in the line y equals x. That is the same as graphing the inverse. So I mentioned that on that one graph where you saw the dotted line going across. That's when you take an inverse reflecting across this line. So that's the same. And then switch the inputs and outputs of the function and graph the resulting function. That is also finding an inverse. So the different one is B. And reflecting across the x-axis is just changing the y values to negative values or making them opposite signs from what they were. That's not what taking an inverse means, at least when it comes to functions. So those are the same. It's different. They don't ask us to explain, but I'm telling you right there. Okay, so we're about to move on to the problem set here. It's numbers 3 to 31. Haven't done them yet, so hopefully they go pretty well. I'll see if I have to graph anything. That's what tends to slow things down a little more than anything else. So let's go ahead and take a look. All right, we're going on to numbers 3 through 8, finding the inverse of the relation. So we saw a set of ordered pairs before. Our idea of finding this inverse is writing out the inverse itself. So swapping the x's with the y's. So here on number 3, we're going to go and say, instead of 1 comma 0, we'll have 0 comma 1. Instead of 3 negative 8, it's negative 8 3. 4 negative 3 becomes negative 3 4. 7 negative 5 becomes negative 5 7. And 9 negative 1 becomes negative 1 9. The same applies to number 4. Swapping the x's and y's, no trickery. I just have to write them out. So feel free to fast forward if you think you understand, or pause it if you think you want to try it yourself. 1 2. Negative 3 4. 7 6. 1 8. And negative 4 10. Okay, numbers 5 and 6 are tables instead, where you have inputs and outputs. So I can kind of generate table-looking thing, if you will. That'll be good enough. Okay, so input and output. You swap the inputs and outputs. You see that negative 5 and that 8 here. Bring the negative 8 up, bring the negative 5 down like that. Excuse me, to bring the 8 up and the negative 5 down. So this will be 8 as the input, negative 5 as the output for its inverse. And then 6, negative 5. You might as well just go across instead of doing this. So see where it says 0, 6, 8 on the bottom? I'm now going to put 0, 6, 8 on the top. So 0, 6, 8. And as long as you organize the rest, the others will be 0, 5, and 10. Probably a little faster if you know those numbers there. All right, number 6. Same thing as before. I guess the idea is I practice one, then you practice one, and that's all good and fine. At least it's systematic that way. Input, output. So let's do this in that sequential order. 2, 5, negative 1, 10, negative 2. 2, 5. So those are your new inputs, and now your outputs are negative 12, negative 8, negative 5, negative 3, negative 2. Simple as that. Takes care of itself. And that's for numbers 5 and 6. Numbers 7 and 8. I'm not going to spend too long on this idea of what these are. Hopefully you've seen them before. These are known as mapping diagrams. A mapping diagram shows your domain values. You see where it says input and output? I want to be even more specific. This represents domain values and range values. The main difference between stating input, output, and domain range, and I'm not calling the book wrong, I'm stating that the reason why you might want to say domain and range with this is because domain lists your elements in a mapping diagram only one time each, even if they repeat as numbers. I'm trying to see if there were repeats before I make this example. Okay, you see on number 5 where you had negative 5 as x that appeared twice. On a mapping diagram, negative 5 will only appear a single time, and what you'll have in its place is multiple arrows mapping to the same value, like this 1 is hit twice as an output for 2 different inputs. That means that 1 would technically have been written twice in a table, even if the table is written vertically. And see how the 7 is written once, but it has 2 arrows mapping out from it, then 7 would have been written twice in that case. And that's what domains and ranges do. They only list every element in the domains and ranges just once each time. Anyway, so that's what the mapping portion is. That means there's a point on this graph. I said I wouldn't explain it. There's a point on this graph that's negative 3, 9, negative 1, 1, 1, 1, and 3, 4. Now, if I swap it, it's going to go ahead, instead of being the output 9, 1, 4, the input's now going to be 9, 1, and 4, and the output is now going to be negative 3, negative 1, 1, and 3. I personally prefer to write these in numerical order, but in this case, I think they want the arrows to line up a little better. So negative 3 went to 9 before, now 9 goes to negative 3. Let's use a different color. 1 came from negative 1 and 1, so now 1 goes to both of those. There's now that split. And now 4 goes to 3. And the original was a function. This inverse is not a function because one input gave you 2 different outputs. Number 8 is the same thing. Just go and swap. You'd basically swap the input-output, guys, but make sure that the arrows go that way from left to right. I should probably put input and output, but I want to be... Whoops, I didn't swap them. I was just copying and pasting. Sorry about the size. 0, 2, 7, 15. I was looking too much at the diagram and not thinking about what to do there. All right, 4 goes to 0 because 0 went to 4. Negative 5 goes to 2 because the other way. 0 only goes to 7, and as does negative 1 instead of splitting off, and 11 goes to 15. So that would be the concept of the swapping when you take its inverse, and that's it, and that's all. Okay, numbers 9 through 12. We are going to solve for x in these scenarios and then find the input. So these are not quite, it is the same as finding the function. We just are the inverse. We're just not swapping x and y meanwhile. So they're having you practice the concept. This is probably lesser of an actual practice when it comes to later testing. I shouldn't say that for sure. It depends on your teacher, but I often wouldn't see a thing like this. Early practice. All right, number 9, f of x equals x plus 5. Let's turn the f of x into y. I'm used to swapping x and y right now, but let's solve for x. Let's subtract 5 from both sides. You'll get y minus 5 equals x, or x equals y minus 5. Okay. So the input is now the one that we are going to be solving for by substituting values for the output. Let's find the input when the output is 2. So let's substitute 2 for y in this scenario, and we will get negative 3 for x. So we have solved for x when y is 2. It's the other way, and so now y is kind of like your input, the way that it would in inverse. Number 10, same thing. F of x equals, we will substitute y in its place. 2 steps to solve for x. I'm going to add 3 to both sides, and then divide both sides by 2. And if you don't mind, I'll just write x on this side already. That's y plus 3 all over 2, like so. Now let's substitute 2 for y, and let's solve for x. That becomes 5 halves, and I'm fine leaving that as an improper fraction. Your teacher should be fine with that as well. Number 11. Trying to find a different color. F of x equals 1/4 x minus 1. Same biz as before. Don't be too freaked out by the fraction. It just means division. We're going to start by adding 1 to both sides. And 1/4 x means x is being divided by 4. I mean, you multiply by its reciprocal, which is 4 over 1, or just 4, depending on how you want to put it. Just make sure 4 multiplies with both terms, just like 2 divided from both terms here. Now 4 multiplies with both terms, parentheses like that. So you can either write it as 4 times the quantity y plus 1, or you can distribute and get 4y plus 4, kind of like that slope-intercept form thing. And then we're going to substitute 2 for y to find the input when the output is 2. When the output is 2, the input seems to be 8 plus 4, which is 12. Okay, and then the last one, number 12, f of x equals, okay, it's good I mentioned reciprocal because it looks like this is going to do that. F of x equals 2/3 x plus 4. Swap them up. It's not swap. Replace f of x with y. And then subtract 4. And then, once again, you could say divide by 2/3, but that does mean multiply by 3 halves. So multiply this side by 3 halves. 3 over 3 is 1. 2 over 2 is 1. You're left with x. Multiply this side by 3 halves. Parentheses. I will go ahead and distribute this one. This will give us x equals, so 3 halves y. And then 3 halves times 4 is 6. So minus 6. All right, let's substitute 2 into there. 3 halves of 2 is 3. And 3 minus 6 is negative 3. Okay. All right. So that's the first, that's 3 through 12. In exercises 13 and 14, graph the inverse of the function by reflecting the graph in the line y equals x. Describe the domain and range of the inverse. Okay. Y equals x is y equals 1x plus 0, a slope of rise and run of 1 starting from the origin. Basically a great diagonal line looking just like that. When we reflect across here, I mean, I wouldn't do it in the literal way, as in trying to see what it looks like as a reflection. You could. I'm just going to be swapping the x and y values for each thing. There are a lot of ways you can go about, making that happen. And I'll go ahead and do it on this page, if that's okay, instead of just using the white, because it's there. Why not? So this point was 2, 4. There's an inverse point that's 4, 2, like that maps with that guy. This one is 4, 5. So we'll have a point that's 5, 4 here. And you can see that reflection. 0, 3 has 3, 0. And we're not really going to fit much else. Maybe that's why they want us to use our own graph paper or something. Maybe I should have. Maybe I should. I will for the next problem, okay? So this is negative 2, 2. We're going to now have 2, negative 2, which I can kind of fit right there. And you see this idea. So I'll go ahead and complete the one here. Next time I'll actually do it on my side with the graph paper. Oh, I don't want it dotted though. So hopefully you can imagine that. Now they ask for the domain and range. This goes forever left and right, and it goes forever up and down. The domain and range are both all real numbers. There's more that I want to say about it, but it doesn't apply for this specific problem uniquely in a way that we can see it for sure. But I'll go ahead and say it. Because the inputs and outputs are switching, whatever was the domain for the original becomes the range for the inverse, and whatever was the range for the original becomes the domain for the inverse. But this happens to go forever left and right as well as up and down, so the domain and range of this is also all real numbers. So they're both sets of all real numbers. Okay, we are going to go on to number 14, and this time, I don't know, I can fit this on the graph pretty equally. I'll just go ahead and graph it here. It seems to mostly fit without problem. I say that, and yet this first point won't really. But negative 3, negative 1 becomes negative 1, negative 3. It's only down there. That's not too bad. Negative 1, 1 becomes 1, negative 1. 0, 2 becomes 2, 0. 1, 3 becomes 3, 1. 2, 4 becomes 4, 2. And those are the only points that I can see. So I'll go ahead and just draw it from that. Looks like so. Now I didn't draw the line y equals x yet. I'll go ahead and do it now by actually just copying and pasting this one. Copy, paste, and place it right there. Looks good enough. And you can see that reflection. It's a different kind, but it works out. Domain and range is still all real numbers for the same reason as before, as is the original. So I wish they had a way to find something unique, but I guess they're trying to keep them linear because we haven't practiced graphing quadratics or square roots or anything yet. We have done absolute values. Or they could have given us one. Listen, these weren't equations. They could have given us any curve under the sun. I would have been happy to play with that. But that's okay. Okay, in exercises 15 to 22, find the inverse of the function, then graph the function and its inverse. Okay, this time I will be using the other side for pretty much everything, including the graphs. So now we actually have to make some work happen. Okay, the thing that we did before, this is going to be number 15. The thing that we did before will apply here. F of x will be y. But what I'm going to do next is from here, now let's swap x and y. This is where we actually apply the inverse process itself. X now equals 3y. This itself is already now the inverse of this. They are now inverses. As in, if you went to your favorite graphing calculator online, I tend to use Desmos, and you typed y equals 3x and you typed x equals 3y, you'll get two lines where they look like they reflect across the line y equals x because they do. But for our sake, when it comes to graphing, we use slope-intercept form, y equals mx plus b, blah, blah, blah. We want to get y by itself in this equation, which means divide both sides by 3, and x over 3 is the same thing as 1/3 x. So y equals 1/3 x is that version of the inverse. I don't know if they would ask you to use g of x. They don't seem to say that here. I could either say g of x equals 1/3 x, therefore. I can use that as well, but it doesn't look like inverse that way. Neither does this. My favorite one is this, the inverse of your function. I really prefer that one personally. This still means y equals, but this is y as the inverse of that function. So you'll see me write that if you don't mind. And we're going to go and graph this if you don't mind. So kind of as best as I can fit it with my room. The function and its inverse. Let's make this one, next time I'll turn it all green when we get to that stage from the get-go. So original function will be blue. 3x plus 0. Y-intercept of 0, rise 3, run 1, like so. Now, before I even draw the lines, I want you to see this for what it is, and then check out the green one as well. 1/3 x, y-intercept of 0, up 1 over 3, like this. And you'll notice right off the bat, before you see any other points that connect, the points that are inverses of each other. 3, 1, and 1, 3, things like that. So hopefully you kind of get that gist. So here is the inverse. Here is the original, and there is an arrow on that other side, you just can't see it, and that reflects across the line y equals x, and we're all good. Okay, that's 15. All the other ones will be the same format. We just have to make sure we find the inverse properly. These look like all linear equations though. Let me get the graph out there first so I know how much room I have. Number 16, we now have f of x equals negative 5x. Y equals negative 5x, and now let's apply that inverse by swapping x and y. We get y by itself by dividing both sides by negative 5. 1 over negative 5 is indeed negative 1/5. So negative 1/5 x is the inverse, or with inverse notation involved, which the book didn't happen to show. Maybe they will in a different problem where they like explore it and say, note that it looks like this. We've seen that kind of thing before. Okay, I'll just go ahead and try and draw it straight up. We are going to y-intercept of 0, and we'll go down 5 over 1, down 5 over 1, like so, and up 5, left 1, up 5, left 1, like that. The inverse is down 1 over 5 from the origin. Boom, boom. And then up 1, left 5. Boom, boom, like that through the origin. Again, tilt your head and see if it looks like those are inverses. They should apply. Okay. Number 17. F of x equals 4x minus 1. Now this will take 2 steps once you've gotten to the inverse in getting those terms over. So y equals, now let's swap x and y. X equals 4y minus 1. We will add 1 to both sides to begin with, and then we will divide both sides by 4. Now, I could write it as x plus 1 all over 4, but for my benefit, this isn't in slope-intercept form, so maybe it doesn't give me the best version of that. So first thing I'm going to do is turn this into inverse of f, and then I'm also going to split this. Instead, x over 4 plus 1 over 4, or 1/4 x plus 1/4, like that. Now, it's still not my preferred kind of problem because the 1/4 y-intercept, but we'll have to go with it. That's literally the inverse, and we'll make sure that it does seem to line up when we do it. Let's start with the blue one. This time I'll actually plot the points again. Negative 1 here, and then up 4 over 1, like so. 1, 2, 3, 4, 1. Now, when they say graph, they don't tell us how to graph it. So here's what I could do. If I really did have trouble with that particular y-intercept and didn't want to do it, I could just flip-flop these points. And here's the point that I did want to make. Remember, inverses. The y-intercept of this was negative 1, but what is its x-intercept? What's that guy right there, that fraction? Remember how we went up 4 over 1? This 1 is a quarter of the way up, so this would be a quarter of the way over. This point is 1/4, comma 0. What do you think its inverse is? 0, comma 1/4. That's what this y-intercept is. That's a little crazy of a point. You know what other points I could use and go off that? See how this one is 1, comma 3? I can use 3, comma 1. That might not be up 1 over 4 from this, but I don't care. It's a point that's on the line. And from here, I can go up 1 over 4 like that. Even if, or I could reflect these, but I can do, whoops, that's not over 4. Up 1 over 4 like that. This should be a reflection of that point, like this. And then I can go down 1 over 4 like that. That's x-intercept, y-intercept, and it just keeps going. So they don't tell you how to do it. I don't need to be told how to graph. And that's the cool part about it. It's not just that there are other ways to do it, but you learn about it by manipulating in different ways. Okay, number 18, and it looks like we'll have more of those fraction things along the way that I can take advantage of it the same way. So f of x equals negative 2x plus 5. Let's turn that into y. Let's swap x and y. Let's subtract 5 from both sides and solving for y. And then let's divide both sides by negative 2. Now I'll do this in multiple steps so you pay closely attention to it. Negative 2, right? So let's turn this into inverse of 1 over negative 2 is negative 1/2, so negative 1/2 x. Negative 5 over negative 2 is positive 5 over 2, which is also 2.5 as a y-intercept. The original is negative 2x plus 5. So from here, let's try and do down 2 over 1, down 2 over 1, boom, 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 like that. I probably should have actually hit the points because it helps me with my other graph, but let's try it without it as well. Plus 5 halves, so 2.5 right here. There is a point on, if this is 0, 5, then there will be 5, 0. So maybe I can actually work off that one. Remember, work off any point you want. You don't have to graph off a y-intercept. The y-intercept is just a nice reference point because you can see the value. But I know this one. So down 1 over 2 like so, and up 1 over 2. And you'll see it kind of go through there properly. So I'll go ahead and draw the line from that. Okay. Okay. And there's that other one. Hopefully you double check all these and make sure they look like reflections across the line y equals x. As a recap, what is the line y equals x? It is this guy right here. And one way you can kind of tell it's a reflection, there should be, if there's overlap, they should intersect on y equals x. That's the only way that it's possible for the x and y to be the same and to swap and still be the same. I have to reformat this. Okay, number 19. 4 more of these. F of x equals negative 3x minus 2. Sorry. Let's go and swap x and y. Now, these are only linear equations, so when you hit integrated math 3, you are going to be doing more with quadratics and cubics and things like that on these. They can get a little hard. I have a video somewhere, and I should link to it and say, you want really hard ones, like even, like not hard, but ones that they take a while to even check on. We could get to those as well at some point. Anyway, I'll add 2 to both sides. I mean, you wouldn't really know what to do with them at this level, but it would still be fun. X plus 2 over negative 3, and then that's negative 1/3 x minus 2/3. Okay, so the same idea as before. If that negative 2/3 seems cumbersome, you can work off of this one, swap one of the other points that's not the y-intercept, and use the negative 1/3 slope off of that. So let's try that. Negative 2 is this y-intercept, down 3 over 1, up 3 left 1. And before I draw that line, let's try it with this one here. Pick a point, like negative 1, 1. There should be a point on the inverse that's 1, negative 1. And now apply that slope down 1 over 3. And it'll cross negative 2/3 for you. Check this out. Up 1, left 3. That's going to cross at negative 2/3 just fine. So that's where a function and its inverse can help each other out when it comes to graphing. See, negative 2/3 looks appropriate across y equals x. Okay, 3 more. Number 20. Y equals 2x plus 3. Make the swap. This is the inverse, remember. If you graph this on Desmos, it will be the inverse that we're going to see on the graph itself. Subtract 3 from both sides. And divide both sides by 2. Let's see if we can write this in one step now. Turning into this already. X over 2 is 1/2 x. Negative 3 over 2 is negative 3/2. Does that feel okay? I hope so. Still fractions. I'm less concerned because I'm going to be graphing this anyway. So positive 3 and up 2 over 1. And I don't know if you follow in the info in the description section on my video itself, I provide you with not only this textbook thing, but also this, graph paper, meaning paper with this scale of axes if you'd like to follow along exactly, or at least go like, whatever. And maybe your teacher provides some for you as well. Let's pick 3, 0, as we had 0, 3, and go up 1 over 2 now. You see it hit that point together. Green. Okay. There are those two. I have 2 more on this part. Number 21. Y equals 1/3 x plus 8. Let's swap that. I should have written f of x equals. Sorry. And then let's go ahead and swap that. X equals 1/3 y plus 8. Okay, subtract 8 from both sides. And y is being divided by 3, right? So let's multiply both sides by 3. So this will be 3 times the quantity x minus 8. If you distribute the 3 in slope-intercept form, we get 3x minus 24. This is a great example of... there are times where fractions might be cumbersome, like 1/2 and 3/5 and whatever, but they're doable. Negative 24 is not in this window range. That doesn't mean the rest of the graph isn't. Part of it will be, because in this one it will be, and it's going to reflect across the line. So let's definitely bank off of this to find a reference point and do it. Negative 24, I'm not going to find it, and I don't want to extrapolate off of it. So I have 8 here, and rise 1, run 3. And fall 1, run 3 to the left. Now these would intersect at some point down the line. No pun intended. But, you would actually get close to seeing where they are, but sometimes they're out of reach. So this one is, again, negative 24, way out of reach, but this will rise 3, run, 1, and it'll kind of look like this. So let's find a point. Instead of 3, 9, we'll use 9, 3 as an inverse value. And let's do the rise 3, run 1, and fall 3, run 1 scenario. And we won't see it hit negative 24 on the y-axis, but I can assure you, with an arrow drawn, it does. And with this accuracy in this perfectly straight line, it does. There they are. Why does that one look longer? Do I just need to extend it more, I guess? Yeah, there we go. That looks a little more symmetrical. Looks a little off. Okay, last one, number 22. There are more problems, but these are the graphic ones. And I don't know what comes next. I haven't seen these, so I always apologize. I was telling some of my other colleagues, I was like, there's going to be a time I just won't know how to do a problem, and I'll just have to pause it and say, I'm moving on. I don't know. So we'll find out. These should be fine for now, though. Okay, f of x equals negative 3/2 x plus 7/2. All right, let's swap it. Where is this going? Because this one has, check this out, this one has the fraction. I'm wondering if the other one won't. And then we can work off of that a little better. So let's swap that up. X equals. Okay, there are plenty of ways you can go about this. We need to solve for y. You could subtract 7/2 from both sides right now. My personal preference when I have a fraction in more than one term, at least one that doesn't, involve the variable, like this guy here, is I'd like to bust the fraction to begin with. So let's multiply everything by 2. Let's do this whole times 2 here. Make this side twice as large, which basically gets rid of those 2's. And in turn, I'll have a 2x over here. So now I have 2x equals negative 3y plus 7. Much cleaner to work off of, even if things turn into fractions later. So I'll subtract 7 over. And then I'll divide everything by 3. It doesn't look like we'll get what I was hoping for, which was a non-fraction in the y-axis. But we'll deal with it. So this is the inverse of n equals 2/3 x minus 7/3. So here's the equation. I'm still mostly going to work off of this one. 7/2 is just 3.5. Not too bad. And I could apply that properly and get an integer value. I'll try and do that for you. So 7/2. 1, 2, 3.5. You know, if you go down 3 over 2 each time, it's going to do that. But 3/2 is also 1.5. So if I go down 1.5 and over 1, then I've hit a point there. That doesn't mean I have to keep going down 1.5 over 1. Now I can do down 3 over 2 and just stay on integer values the rest of the way. And then I can use those for the other portion of this graph. So from here, up 3 over 2. And I've satisfied kind of my need for that. So, sorry, for those who are aware from an older video, my head's getting at me now. Having a little bit of trouble. There was the point 1 comma 2. Let's go to 2 comma 1. And now let's apply the 2/3 slope. And it's positive. So up 2 over 3. See, that seems wrong. Something should be, did I mess something up there? Negative 3. Oh, I'm sorry. Let me fix this. Let me do this. Hold on. This was a negative 3y. We got to divide by negative 3, and that'll turn negative and positive. When I was saying it's a positive slope, I said something looks very wrong there. So let's try that again. This will still be here, 2 comma 1. Now let's go down 2, right 3. There we go. That looks better. So something's off. See, if you know inverses, then you'll be aware when something doesn't look like it's supposed to. There we go. Okay. And that should cross 7/3. That 7/3 is 2 1/3. So that should be crossing that area when we draw this line with your ruler or a line tool. So not only does it look like it kind of gets that proper reflection, but this crosses at about 2 1/3, and that's looking good. Okay. That's the end of those ones. Let's move forward to... All right, hey guys, Mr. Robinson back here with the recording. Something happened as I was recording this video. My computer went and completely crashed on me. And in a way that I'm certainly glad that everything that I was able... Not everything I was able to record, but most of what I was able to record is mostly functional. If you saw some parts and hitches earlier on, I apologize for that. I didn't know they were happening. They didn't show up on my end. Eventually, my stuff stopped responding as I was talking, and then everything just went up and crashed completely. I'm just glad that what I was able to retrieve from the video that's functional is still actually there. And, I value my time of it. I value your time as well when it comes to this. So I'm going to... let's see, my video that I have on there, even though it doesn't play right, went to about 47 minutes. So whatever time you're looking at right now is the time that I lost. So I'm going to kind of just make up that time with what was written on my thing. And I hope everything that you saw before, even if it froze a little bit, isn't too bad. So really, again, I'm sorry about that. And let's see where we are at, basically. So I did numbers 23 and 24. I guess that's the only real information that I lost video-wise, and I'm just going to go back and show you what I wrote at the time, if that's okay. Because this troubleshooting took a while. I even had to switch hard drives that this is recording to now for it to even work correctly. And I'll have to do some post-video editing, which already happened now that it's uploaded. Okay, number 23, error analysis. Describe and correct the error in finding the inverse of the function f of x equals 3x plus 5. So you'll see they turn f of x into y, which is good. And then in a situation where you'd want to get the input by itself, this would be okay. But if you want to find the inverse, you're supposed to be swapping x and y before you go and do subtract 5 and divide by 3. Which they did all of that just fine, but they did not swap x and y. So that's what I put here. So x and y never swapped. The input needs to become the output and vice versa. So instead, you should be swapping x and y, then subtracting 5 and dividing by 3. Instead of using g of x, I just wanted to mention that I'm going to keep using my inverse notation. Either or is fine. I like this one more, just stating it actually works as an inverse. So there's number 23. Number 24, error analysis. This is my fix, so let me get rid of that for a second. Describe and correct the error in graphing the inverse g of the function f. So you look right here on this one in number 24, and f is the original, and g is what they propose as the inverse. They reflected across the line all right, but they reflected across the line across the x-axis. So the y values turned to their negative sign what they were, instead of reflecting across the line x equals y and swapping the x's and y's. So that's what I put here, and I said they reflected across the x-axis, changing y signs instead of reflecting across the line, and then I drew the correction, if you will, right? I think, what, like that? I think like that. So if you ignore the red, you just look at the green and the blue are what work together as inverses, and that would be proper. What was 0, 2 becomes 2, 0. What was 3, 0 becomes 0, 3. And what was negative 3, 4 becomes 4, negative 3. And then I drew and connected the lines there. So that's pretty much what was lost for that, and I hope everything here is recording just fine and won't crash on me again. I have to check that other hard drive and see how it's going on. Then I was reading this problem, trying to write something, and then it went up and froze. So let's go ahead and see if we can get past that barrier. Okay, number 25, modeling with mathematics. The euro is the unit of currency for the European Union. On a certain day, the number E of euros that could be obtained for D US dollars was represented by the formula shown. Oh, much better. As I was writing the E, there was a problem. So 0.74683. So the euro is about 75% of the dollar, if you will. Solve the formula for D, then find the number of US dollars that can be obtained for 250 euros on that day. So if we divide both sides by this, then we'll say that D equals E over 0.74683. This is a way of, I didn't necessarily get the inverse here, but I swapped the input, solving for the input versus solving for the output. Now my euro is going to be the input to get an output for D, instead of my dollar being an input to get the output E, if that makes sense. So 250 euros for gets you how many dollars D, and this is where we would need a calculator. I actually didn't prepare that part. Let me use my phone for that. Give me 1 second. And we'll round to if it's a rounding thing, we'll go ahead and round to the nearest cent, unless they ask for something else. They said the number of dollars. I'll put decimals. So 250 divided by 0.74683 is getting me 334 point, and there are a lot of decimals. It probably goes on forever, but 7482 is good enough there. So I'll say $334.75 about, if I round to the nearest cent. So that's how many dollars converts to 250 euros, and that'd be the answer. Are we still going? Okay. I hope. Oh, I'm missing something on my set. Can you see that now? There we go. Okay. Here we go. Number 26. All right, modeling with mathematics. Why not? You work at a manufacturing plant and earn $11 per hour plus 50 cents for each unit you produce per hour. Write a linear model that represents your hourly wage as a function of the number of units you produce per hour. Okay, so let's use like x and f of x or things like that, because it's going to be a function of something. So we'll let x equal number of units produced. In an hour, per hour. And then f of x equals total amount earned, hourly wage in dollars. Okay. So this f of x equals, we have a starting amount, if you will, y-intercept, $11 per hour, and that's just that flat rate. That doesn't change no matter how many units you produce. And then $0.5 per unit produced times the number of units you produce will get you that. So this is a good linear equation, y equals mx plus b form. That's what we're kind of looking at. That would be a good part A. Part B, find the inverse of the function you wrote. What does each variable in the inverse function represent? So it's good that I define the variables here, because then we can go ahead and do this. I'll turn f of x into y. Those are interchangeable. That's fine. But if we're going to go and take that inverse, let's swap the x and the y. Okay, and then let's go and solve that. subtract 11, and then we can divide both sides by 0.5. Now y equals x minus 11 over 0.5. This is one version of it you could write. If you are kind of a math hound like I am, we're not really big on decimals with fractions. Yet I say that in the dollar thing we could, but decimals we can turn into non-decimals if we wanted to. 0.5 is the same thing as 1/2. Dividing by 1/2 is the same as multiplying by 2. Dividing by 0.5 is the same as multiplying by 2, meaning this is equivalent to that, 2 times this thing, or 2x minus 22. I kind of like that version more. So inverse, that's my favorite way of writing this version right there. The y, the inverse of, however you want to put it. So find the inverse. What does each variable in the inverse function represent? This time we swapped what was the input and output. The inverse now tells you how many units you would produce if you earned this many dollars. So now x is the hourly wage. And this new y represented as inverse of your function represents number of units produced per hour. So now it's like, hold on. You know, there's some version of this that you start making units over and over. You're like, whew, I'm done. Okay, I made 10 units. How much money will that be? Great. Now maybe there's another day that you're like, you know, I really need to make $15 on this day. How many units would I put? You know, like that kind of thing. And then you can figure out, oh, I need to make this many units. So changing the independent and dependent variables in that situation kind of works out sometimes. All right, part C. What is your hourly wage when you produce 8 units per hour? It's recommended in this situation, if hourly wage is your dependent variable, that you use the equation from part A that you made. Hourly wage based on this many units. So if we produce 8 units, we should do f of 8, which is 0.5 times 8 plus 11. 0.5 times 8 is 4, and 4 plus 11 is 15. Oh, that's that $15 thing. So your hourly wage will be $15 if you produce 8 units in that hour, per hour. Part D, how many units must you produce per hour to double your hourly wage in part C? Okay, so part D, double equals $30. And you'd be forgiven if you believed you would just need to make 16 of these units. But keep in mind, you didn't make $15 from producing 8 units. You made $15 from the 8 units plus the $11 in the per hour thing. So this is another part of it. So instead what you should do is use your inverse equation, just the reason that I explained before. Use the inverse equation that we have here. Let's find the inverse, because now x is our hourly wage. We find out an output, y, based on that input. So let's do inverse of 30. That equation was 2x minus 22. So we'll do 2 times 30 minus 22. And this should tell us how many units we should be making to get $30. 60 minus 22 isn't 16, but 38. So you need to produce 38 units per hour in order to get that hourly wage of $30. That's a lot. It's a lot of units. I mean, not a lot of money. All right. Well, per hour, actually, that is pretty good. All right, open-ended. So it's not just what I say, and I don't know what it is yet, but let's figure out what it is. Write a function such that the graph of its inverse is a line with a slope of 4. Okay, so if I have some sort of... Now, here's the thing. An inverse of a function... Excuse me. As an inverse of a function is an inverse of a function, the function is also an inverse of its inverse. See what I mean? So the reason I bring that up is because maybe they're tricking you with the wording. They could also say, write an inverse such that the graph of its function is aligned with a slope of 4. I don't care which one's the inverse, which one's the function. If I write this as f of x or inverse of f, I'm still just going to talk about the inverse is aligned with the slope of 4. Okay, here's one. But if you have trouble looking at the inverse, that's not the answer. I'm saying that's an inverse. Let's say we look at it as the function for a moment, then I'll swap it up. Let's say this was it, or open-ended. Let's play with it a little more. Let's put plus 8. Okay, here's a function. Let's take its inverse. Sorry if you hear a humming. Give me 1 second here. Okay, here we go. Y equals 4x plus 8. Swap x equals 4y plus 8. Subtract 8 and divide both sides by 4. You get y equals 1/4 x minus 2, or the inverse of. Right, so all that happens, blah, blah, blah. Okay, that's taking an inverse with a function. Now, they said write a function so that the inverse is that. Okay, see how I said this was a function? I lied. This is an inverse, and, oh, this will be the function. There we go. Okay, I came up with one. So, what are we actually seeing out of this? It looks like we just needed the reciprocal slope. This was a slope of 4. This is a reciprocal slope of 1/4. Does that always apply? For linear functions, I think so. For other functions, they don't always have slopes, so that doesn't really work. But this is an example of one. I'm just kind of giving you that heads up on what you could do and how you could perceive it. That's my version of it. This was open-ended, and feel free to do what you like on it. All right, the last few here, numbers 28 to 31. Number 28. Pair the graph of each function with the graph of its inverse. So what we could do is kind of play off that slope concept. I think that'll work. When I see a slope here of up 3/1, then I should find one with a slope of up 1/3. That doesn't mean it guarantees it's the inverse. It also needs to, intersect things, right? But when I see A, I think E, whoops, let me write it over here. When I see A, I think E also applies here. So you look at A and E, you see that this is a slope of, what we really should do actually is just find points that seem to be inverses instead of the slope. I just wanted to play off the previous problem, but you see that right there. It's that there's a point that's 1,3 and a point that's 3,1 and things like that. So I think A and E work just fine there. B has a point that's 2,1. So let's find a point that's 1,2 to start, like C. And nothing else has 1,2, so that must be it. So B and C. And by process of elimination, it looks like we also have D and F. Let's see if that works out. D has a point that's -1,4. F has a point that's 4, -1. That seems to apply. So that works. Okay, number 29. Oh, critical thinking. Here we go. Consider the function g of x equals -x. Graph g of x equals -x and explain why it is its own inverse. Okay, so let's go ahead and draw this graph. Now, g of x equals -x is simply -1x plus 0, down 1/1 from here, over and over, and up 1 left 1 from here. Okay. Remember, an inverse of a function is the set of points that reflects across the line y equals x, like this. So based off the graph, my explanation could be when you swap x and y, you get the points out on the other side of this reflection. Look at the point -3, 3. When you swap -3, 3, you get 3, -3. And where's that? This point right here, which is still on the line. So these points are reflecting across the line perfectly. It's not the same points, but they exist on the same line as a result of this. And anything with a slope of -1 seems like it would be doing that in that form. And so that's my version. It's a visual explanation with the graph, and what you see is a set of points that the reflected points exist on the line the same way because of the nature of the slope. They asked to explain it through the graph, it seems like, so that's what I'm doing. That was part A. Graph other linear functions that are their own inverses. So I just mentioned anything that still has a slope of -1 should do it. If we're talking about what we mentioned on that previous problem, how the reciprocal slope needs, like if you have a slope of 2, then the reciprocal slope of 1/2 would exist in the inverse function of the inverse of a linear function. So when you have a slope of -1 here, its inverse is still -1. So those slopes still apply, and it still lets you do that. So when they're asking on part B, name some others, come up with some others. Anything that has a slope of -1 that'll work. So -x minus 7, -x plus 20, anything like that. And another one that would work is just y equals x. Literally being right on this line itself, y equals x, because that is the line y equals x that it reflects across. Those are a few. They said graph them. I can't graph the plus 20, but here would be -x minus 7. And the line y equals x is the black line right there. That's the idea. That was not part A, that was part B. Part C, use the results from part B to write a general equation that describes the family of linear functions that are their own inverses. Y equals negative x plus b. So generally, as long as this is some y-intercept value, it doesn't matter. B is some y-intercept value, as long as your slope is -1, you're taken care of. This one is very specific for this positive slope. It needs to be that specific one right there, and then it'll work out. Maybe I should ignore it for the sake of what they're asking me to do. Okay, number 30. Thought-provoking. Find a formula, for instance, from geometry or physics, that has an inverse function. Explain what the variables in your formula represent. I know one. A very a very common, popular one. Fahrenheit and Celsius. That has an inverse function. Okay, yeah, okay, well, anyway, we'll just say it. I mean, there are a bunch that you can say. Degrees Fahrenheit and degrees Celsius. Degrees Fahrenheit, I think it's 9/5 degrees Celsius plus 32, like that. If you want to find out, if you want to convert from one to the other, you get that, okay? I don't know if that's what they mean with this, because this is more input-output. Does this count as inverse? Maybe. I'm sure I could come up with so many others, but this is kind of what I'm thinking of. It still has an inverse, but instead of using f and c, let's use y and x so we can kind of give it that inverse bit, and I'll just define them as that. So y equals x. Y is degrees Fahrenheit, and x is degrees Celsius. Okay? Now let's go ahead and, they say find its inverse? No, they didn't. Okay, well, maybe I didn't have to do that. Okay, Fahrenheit and Celsius, but let me say this. Degrees Celsius is from, well, here, let's solve it. Let's solve it. I have time. Swap the x and y. Subtract 32. And then divide both sides by 9/5, or multiply both sides by 5/9, and you get y equals 5/9 times x minus 32. When you write it with, like, Celsius and Fahrenheit, it looks like this. So you can find these online like that. So there's that actual conversion, but that would be the inverse, I guess, written like that if we ever played with it that way. But this time, guys, this time x is degrees Fahrenheit and y is degrees Celsius right there. Okay, or inverse of f. Okay, so that's the idea. There are a bunch of them that you can do, I'm sure. I'm just not playing with them in my head. This is just thought-provoking. You can research it. And number 31, show that the inverse of any linear function, f of x equals mx plus b, where m does not equal 0, is also a linear function. Write the slope and y-intercept of the graph of the inverse in terms of m and b. So we're just using that they have, f of x equals mx plus b. Let's change that to y, swap x and y. See, x equals my plus b is not something that we say. M is no longer a rise over run, now it's a run over rise, and b is now an x-intercept, not a y-intercept. And that's exactly why those things work that way. That's why it's linear, but let's even keep going on it. Let's solve for y. X minus b equals m times y, and divide both sides by m. You get y equals 1 over m times x minus b over m, like so, or the inverse of. Okay, so what did they ask us to say here? They said, show that it's also linear. It is right here. M is a non-zero value, so we're not dividing by 0. That means it can represent a slope. Even if it was 2/3, 1 over 2/3 is 3/2. This is a number over a number, because that's what they were here above, m and b. Write the slope and y-intercept of the graph of the inverse in terms of m and b. Yeah, right there. So the slope is in terms of m, the y-intercept is in terms of b and m. So it's good. Okay, that's it, and that's all. Now I have some editing to do on my end, so that ought to do it for this one, guys. Mr. Robinson, thank you so much for everything that went on, including the chugging. I hope I can address them as best as possible, and I appreciate you. Thank you. Take care.